Witness the epic journey of transporting, installing, and powering colossal offshore infrastructures amidst the relentless force of the sea. Aquatic's powerful new 1500T Carousel system represents a major advancement in subsea product installation technology. Designed to handle up to 500 metric tons of umbilicals, cables, or flexible pipes, this modular system delivers exceptional performance and versatility. With a 12-meter reel diameter and variable hub design, it can accommodate a wide range of product sizes and specifications. One of its key strengths lies in its modular construction, allowing the entire carousel to be broken down into components that fit standard shipping containers. This feature simplifies transportation, assembly, and mobilization, making it an efficient and cost-effective alternative to building a dedicated vessel. The system can be easily installed onto a vessel of opportunity, significantly reducing operational costs and increasing deployment flexibility. Equipped with a built-in tensioner, mounted on a level wind tower, the carousel ensures consistent product tension and precise spooling during offshore operations. Its maximum reeling speed of around 1 km per hour supports smooth and controlled handling of heavy subsea products. Overall, Aquatic's 1500T carousel system combines strength, adaptability, and efficiency, setting a new benchmark for modern offshore installation equipment. At Toliotti Port, a complex heavy lift operation was carried out to unload and handle two massive industrial columns, each weighing 150 tons. The process involved the precise coordination of rail-mounted cranes, specialized modular trailers, and the maneuvering of a cargo vessel. The entire sequence was executed with accuracy and safety as top priorities. The operation began with the approach of two powerful rail-mounted lifting cranes, type EDK-2000, each having a lifting capacity of 250 tons and a boom outreach of 23 meters. These cranes arrived along the railway tracks to the loading site and were carefully positioned beside the quay. Technicians then performed the preparation and inspection of the cranes, including stabilizing the outriggers, checking the lifting gear, and ensuring proper communication between operators. Meanwhile, the cargo vessel approached the berth, carrying two enormous chemical industry columns on deck. Each column measured between 12 and 29.5 meters in length, with a diameter of 3.2 to 3.4 meters. The ship was secured alongside the quay, and rigging specialists attached heavy-duty slings and spreader bars to the first column. Every connection point was thoroughly checked before lifting began. Once all preparations were complete, both EDK-2000 cranes began the lifting of the first 150-ton column in a synchronized operation. The cranes worked in tandem to evenly distribute the load, gradually raising the column clear from the vessel's deck. The lift was executed slowly and steadily to minimize swinging and to ensure that the cargo remained stable. Onshore, A hydraulic modular semi-trailer, part of a heavy-duty road train with a lifting capacity of 180 tons, had been positioned on a prepared platform. The ground surface had been reinforced and leveled to support the extreme weight. The column was carefully rotated and lowered onto the modular trailer, which featured a hydraulic suspension system allowing fine height adjustments. Once the column was securely fastened with chains and supports, the trailer departed slowly toward the storage area. After the first column was successfully moved, the vessel was rotated, positioning its opposite side toward the cranes to access the second column. This maneuver ensured that the cranes could reach the next load safely and within their working radius. During this time, workers prepared the platform for the second column, setting up sturdy support blocks, towers, designed to temporarily hold the cargo. These blocks were precisely adjusted so that their height matched the level of the trailer's loading platform. As the second column was hoisted, the cranes raised it smoothly from the vessel and gently placed it on the waiting supports. The modular trailer then drove underneath the column, and using its hydraulic suspension system, it lifted the load from the supports without additional crane assistance. This method ensured both safety and efficiency, reducing lifting risks during transfer. With the second column safely on the trailer, the cranes were disengaged and folded back to their travel configuration. The trailers then transported both columns to their designated storage locations within the port area, where they awaited further shipment to the chemical plant. The operation at Toliotti port demonstrated the precision and technical capability of heavy lift logistics, combining railway cranes, modular trailers, and marine handling in one seamless process. It highlighted not only the strength of the EDK 2000 cranes and advanced hydraulic transport systems, but also the careful planning and coordination required to move 150-ton industrial components safely and efficiently. The Ulsan Hyundai Heavy Industries (HHI) fabrication yard, located in Ulsan, South Korea, is one of the world's largest and most advanced industrial complexes for heavy engineering and offshore construction. Established along the southeastern coast, the yard covers a vast area equipped with massive dry docks, quays, and heavy lift cranes capable of handling ultra-large modules and structures. It serves as a key manufacturing and assembly site for offshore oil and gas projects, including topsides, jackets, and LNG modules. The yard demonstrates its exceptional capability in handling gigantic structures. The Gorgon LNG modules, each weighing thousands of tons, were precisely fabricated, assembled, and loaded out onto transport vessels using heavy lift cranes and self-propelled modular transporters. This operation highlights the yard's efficiency, precision, and adherence to global safety and quality standards. Today, HHI's Ulsan Yard stands as a symbol of South Korea's engineering excellence and industrial strength, providing world-class solutions for offshore energy development, shipbuilding, and modular construction projects worldwide. From the geotechnical analysis at Darren's port, to the reconstruction of the refinery berth, and from the design of the RORO ramp to the carefully calculated vehicle configuration, Each stage showcased the integration of precision, innovation, and safety. In 2013, one of the most extraordinary heavy lift operations in Turkish history took place: the transportation of a 918 metric ton cracking reactor from Aurora in Japan to the Tüpraş İzmit Refinery in Turkey. The operation began at the port of Muroran, a well-known industrial harbor in Japan. The cracking reactor, designed for the refining process at Tüpraş, was carefully loaded onto a heavy lift vessel specifically chartered for the intercontinental voyage. Due to its extraordinary size and weight, the loading process demanded extensive structural calculations to ensure the ship's stability and trim throughout the ocean crossing. Special sea fastening and lashing systems were designed and calculated in advance. Engineers reinforced the ship's deck structure to distribute the massive load evenly, preventing excessive local stresses. Once secured, the vessel departed from Muroran, embarking on a long journey across the Pacific and through the Suez Canal, finally entering the Mediterranean and heading toward Turkey's Marmara Sea. After several weeks of navigation, the vessel arrived safely at Darent's port on April 24, 2013. The port, operated as a heavy lift terminal, was selected for its proximity to the Izmit refinery and its accessibility for oversized cargo. However, even this facility required detailed preparation before handling such a massive reactor. Extensive geotechnical and engineering analyses were conducted to verify the port's capacity to bear the immense static and dynamic loads generated during unloading. The soil-bearing strength and quay structure were both evaluated. To keep the stresses within safe limits, steel plates were strategically placed under the supporting stools used for the cargo. These plates acted as load spreaders, reducing the pressure on the port surface and ensuring stability during the transfer. The vehicle configuration, consisting of a modular self-propelled trailer with dozens of axles, was analyzed in depth. Engineers carefully calculated stability angles, axle loads, and traction power to ensure safe maneuvering. Every detail, from the hydraulic suspension to the steering geometry, was studied to guarantee a smooth transition from ship to shore. A crucial part of the operation was the ballasting procedure. Since the heavy lift barge's stability depended on controlled ballast operations, this step was guided by specialists. Proper ballasting ensured that the vessel maintained equilibrium as the load shifted during unloading. With all preparations completed and weather conditions favorable, the reactor was successfully rolled off the vessel and transferred to the shore, marking the end of the maritime phase. The final destination was the Tüpraş İzmit Refinery, one of Turkey's largest petroleum processing facilities. The on-site receiving berth at the refinery required significant modification to accommodate such a large and heavy load. In fact, the private refinery berth had to be reconstructed entirely to meet the operation's requirements. The approach maneuver of the barge carrying the reactor was extremely delicate. The area included a gas pipeline finger located dangerously close to the quay, leaving very little room for error. To complicate matters, structural damages caused by a previous earthquake made it impossible for the barge or the transfer ramp to make direct contact with the key edge. To overcome this, engineers designed a special roll-on/roll-off ramp system, consisting of 4 modular sections, each 12 meters long and capable of bearing 500 metric tons. This innovative design allowed the cargo to be safely rolled from the barge onto the quay, without exceeding the structural limits of either. Before the reactor could be moved inland, a series of preparatory works were undertaken. The traction power of the SPMTs was recalculated to ensure that they could negotiate a 5.3% slope along the existing access ramp. In addition, the internal refinery routes were carefully inspected. The turning radius along curves and intersections had to be adjusted to accommodate the transport vehicle's large footprint. Ground conditions were also checked and reinforced where necessary to avoid deformation or subsidence during passage. Once all parameters were confirmed, the final land transport began. The convoy moved slowly, guided by spotters and engineers with every axle synchronized for balance. The transportation inside the refinery grounds represented the most critical and delicate phase, as even small ground irregularities could compromise the stability of the load. Despite these challenges, the movement proceeded smoothly and precisely. According to local tradition, recognizing the extraordinary importance of the operation, the refinery owner sacrificed a ram before the start of the onshore transfer. This symbolic gesture reflected the deep respect and cultural significance associated with such a monumental industrial event. After careful maneuvering and final alignment, the massive cracking reactor was positioned at its designated installation area within the refinery. The operation concluded successfully, without any incident or structural damage, an impressive demonstration of technical skill, engineering coordination, and risk management. The transportation of the 918 metric ton cracking reactor from Modular, Japan, to the Tüpraş İzmit refinery in Turkey remains one of the most remarkable heavy lift projects in the country's history. It combined advanced engineering with meticulous planning, covering every aspect from maritime logistics to civil engineering reinforcement. The transportation of the Haliade 150 offshore wind turbine tower for the Offshore project represented a remarkable example of precision engineering and heavy logistics coordination across 3 European ports. The entire operation began at the port of Avilés, Spain, where the massive steel tower sections were prepared for shipment. The chosen vessel was equipped with a maximum dual lifting capacity of 900 metric tons, ensuring safe handling of each segment. The tower was divided into 3 main sections: bottom, middle, and upper. The bottom section, measuring 30 meters in height and weighing 200 metric tons, was the first to be loaded using a single lift operation. One of the vessel's cranes was specially modified with a heightened pedestal, enabling it to raise the section in a vertical position, a unique requirement for this type of wind turbine structure. The middle and upper sections, each 25 meters high and weighing 104 metric tons, were lifted using twin lift operations to ensure stability and even load distribution. These operations required exceptional coordination between crane operators and rigging teams to maintain perfect alignment and prevent any torsional stress on the tower bodies. After the tower components were safely stowed, the vessel sailed to the port of Montoire, Saint-Nazaire, France, where it was loaded with the nacelle, the heaviest single component of the turbine. The nacelle, weighing 450 metric tons, was lifted using a hydraulic lifting tool in a single lift operation. The precision of this step was crucial, as the nacelle contained sensitive equipment, such as the generator and gearbox. Once fully loaded, the vessel proceeded to its final destination, the port of Hanstholm, Denmark, for the unloading phase. Here, each component was directly unloaded onto specialized hydraulic and SPMT vehicles for inland transport. The nacelle and the two horizontal tower sections were transferred onto hydraulic trailers, while the vertical bottom tower section was placed on an SPMT to ensure stability during movement. The land transport from Hanstholm to the Oosterwolde test field, approximately 22 kilometers away, required meticulous planning and coordination. Due to the size and weight of the cargo, police escort services were deployed, and temporary modifications were made along the route. These included adjusting road signage, reinforcing certain sections, and even reversing the direction of traffic flow in some areas to allow safe passage. The operation concluded successfully, demonstrating the high level of technical capability and logistical expertise required to transport such colossal wind turbine components across multiple countries. It was a key step toward the installation of the GE Haliade 150 turbine, a milestone in the development of next-generation offshore wind energy. The operation begins with mobilization, during which all the necessary tools, equipment, and skilled personnel are prepared for deployment. The mobilization phase also includes the transportation of heavy equipment to the quay and its installation on board the vessel. Next, the process continues with carousel transfer and carousel assembly, where a large rotating storage system is installed and secured. This carousel is designed to safely handle long lengths of umbilicals during offshore operations. After the setup, umbilical reels transfer takes place, moving large spools of umbilicals from storage areas onto the vessel. The following stage, umbilical transpooling, involves carefully transferring the umbilical from reels to the carousel, ensuring even tension and avoiding twisting or damage. Once the vessel is fully loaded and all tests are complete, offshore operations begin. The vessel sails to the designated offshore site, where the umbilical deployment is conducted using precision-controlled equipment, tensioners, and remotely operated vehicles. Through these well-coordinated stages, Subsea demonstrates advanced engineering, operational safety, and efficiency in subsea installation projects. The 170 meters, 584-ton flare boom for Carousel FLNG was lifted and transported from Beaumesque Yard, China, to Shai Shipyard, Georgia in December 2020. The operation to remove the 13 500-ton YME topsides began, as the pioneering Spirit slowly maneuvered in reverse toward the offshore platform. Moving backwards allowed the vessel to achieve an optimal position for installing the cutting tools. These precision tools were mounted inside the 3 vertical legs of the platform, which supported the massive topsides. Each tool was carefully lowered and aligned to ensure clean and controlled separation later in the operation. After the cutting tools were installed, the vessel moved around the YME platform to position itself correctly for the lifting phase. The motion of the sea caused the platform to rotate slightly, so accurate alignment was crucial. Using its dynamic positioning system, the pioneering Spirit achieved millimeter precision while hovering close to the structure. The crew prepared the 5 large lifting yokes on board, which would connect to the underside of the platform to perform the lift. Once the vessel reached the exact position, the first phase of the connection process began. The 2 middle yokes were positioned under the platform first. As the platform continued to move slightly with the waves, the vessel activated its active motion compensation system. This advanced system synchronized the ship's motion with that of the sea, keeping the lifting beams stable relative to the topsides. The 2 central yokes were connected firmly to the structure, immediately absorbing and neutralizing the rotational movement of the topsides. Next, the focus shifted to the 2 front yokes. These were positioned carefully under the forward section of the platform. The motion compensation system was engaged again to keep the vessel's movements perfectly balanced during connection. The crew monitored the hydraulic systems continuously to maintain alignment between the yokes and the platform's connection points. Once in place, the front yokes were locked and fully secured. After that, attention turned to the aft yoke at the rear of the vessel. This final connection was essential to distribute the weight evenly across all 5 yokes. The aft yoke was positioned under the platform with precision, and once again the active motion compensation system was engaged. The connection was made smoothly, completing the attachment of all 5 lifting points. When every yoke was connected and confirmed to be secure, the deballasting phase began. The pioneering Spirit released large volumes of ballast water from its tanks, creating an upward buoyant force. This process generated controlled upward pressure through the hydraulic lifting system, allowing the vessel to preload the structure before cutting. The team monitored the sensors on all yokes to ensure equal load distribution during this crucial phase. Once sufficient upward pressure was accumulated, the cutting tools inside the 3 platform legs were activated. Each leg was cut through simultaneously, separating the top sides from the jacket structure below. The sensors confirmed that the cuts were complete, and the vessel immediately performed a fast lift operation. In one swift and precise motion, the 13 500-ton topsides were lifted completely clear of the legs. The pioneering Spirit then carefully moved away from the remaining substructure. The active motion compensation continued to stabilize the heavy load as the vessel increased the distance to a safe clearance. When the vessel was far enough from the platform legs, the sea fastening system was engaged to lock the topsides securely on the vessel's deck. This ensured full stability during transit through open waters. Following the lift, the vessel began its voyage toward the dismantling yard in Lutlandet, Norway. Throughout the transit, the topsides remained firmly secured, and the ship's systems maintained constant monitoring of the load balance and structural integrity. Upon arrival at Lutlandet, preparations began for the final transfer. The pioneering spirit positioned itself next to the barge Iron Lady, which was designed to receive heavy structures for onshore dismantling. Using a combination of ballast control and precision alignment, the vessel gently lowered the YME topsides onto the barge. The transfer was completed smoothly, marking the end of the removal operation.